Honorable President of the Republic of Estonia, dear guest, Professor Kurt Wüthrich, dear Endel Lippmaa, ladies and gentlemen, the essence of science is, of course, looking beyond our horizon of knowledge, but also looking legally into the future. And this is, however, only possible based on perfect knowledge of the past and excellent recognition of the problems to be solved today. Already Isaac Newton stressed that those who are standing on shoulders of giants have much better perspective, and it is important that those giants are identified and recognized. Like Germans used to say, you should always take time to say thank you. It's a long tradition in scientific community to recognize those who have essentially advanced our knowledge. Probably the oldest surviving scientific award in the world is the Copley Medal, first being given in 1731 to Stephen Gray. A similar tradition has been continued for decades also in the Estonian Academy of Sciences, but the recognitions made by our Academy have mostly been designed for Estonian scientists. This is too another viewpoint in the contemporary world where science is intrinsically international, or even be better called global. Today, we have the honor of being part of the first international award issued by the Estonian Academy of Sciences. This is named after academician Endel Lippmaa, who was one of the most prominent representatives of Estonian science and politics, and until today, one of the most well-known Estonian scientists in the world. What is important that he significantly contributed not only to science, but also into the process of regaining independence of Estonia and building of democratic society in our country, how we feel today. To recognize his exceptional contribution, the Estonian Academy of Sciences is willing to establish the tradition of memorial lectures and memorial medal of Endel Lippmaa. We wish to recognize not only excellent science, but also equally the role of scientists in the development of society. And following these principles, we invite to present Endel Lippmaa Memorial Lecture excellent scientists or those who have made significant contribution to the development of society or have made both. We first of all would like to underline the importance of serving society by eminent scientists. It is my pleasure to announce the first recipient, lecturer of Endel Lippmaa Lecture, Professor Kurt Wüthrich. He is a Swiss chemist or biophysicist and Nobel chemistry laureate known for developing nuclear magnetic resonance methods for studying biological macromolecules. But it's not about him today, it's about serving society by science. Science, along with culture and sports, is a substantial component of the face and reputation of each country. And Germany has even positioned a few years ago science diplomacy as a part of their official foreign policy. And presidents of Estonia have been traditionally either scientists or very close to scientific landscape. I'm happy that our President, Mrs. Kersti Kaljulaid, continues this tradition and will now introduce today's lecture.
Dear Professor Wüthrich, my sincerest congratulations to you on receiving the first Endel Lippmaa medal. Endel Lippmaa was a brilliant scientist and member of this Estonian Academy of Science, but he was indeed much more to us Estonians. He was adept, sharp, and astonishingly convincing mover in the corridors of the enemy. Having honed his capacities convincing the Soviet system to finance his ambitious scientific projects, he gave this knowledge to the service of Estonia when it really mattered. He was among those who managed to extract from Communist Party an acknowledgement of the pact between Hitler and Stalin signed by Molotov and Ribbentrop. It was an extremely important step, as by this acknowledgement the common position of the communists that Estonians had voluntarily joined the USSR was overturned. Professor Lippmaa had iron logic and ample supply of facts, all nicely arranged in his brain and physically on his shelves or in his big portfolio, which he never hesitated to pull out at the right moment to kill the less informed arguments of his opponents. He clearly had big influence on the quality of the political debate in Estonia, freshly relieved from the occupation. I am so glad and proud we finally honor his memory by establishing this tradition of medal ceremony accompanied by a lecture. I am sure he would have loved this more than a monument standing alone and silent somewhere. I believe, Jaak, you can verify my words. I'm sure he was fond of people, fond of discussions, arguments, counter-arguments, active verbal combat. Professor Wüthrich, I am glad that the selection committee has chosen you to be the first laureate of the Lippmaa medal. You, as Professor Lippmaa, have been fascinated by the nuclear magnetic resonance. You have both contributed to our ability to understand how life really works. Your work in particular has allowed humankind to look into the structure and dynamics of proteins without removing them from their natural environment. Solution. I have to confess that as an interested but not too knowledgeable follower of the developments in biochemistry and our understanding of the roles of different proteins in the functioning of a cell, I have seldom thought about how we get to know what we know. And reading through your lecture from the time you received the Nobel Prize focused my mind really sharply exactly on this issue. Trust for the scientists in our community, scientists' role in our community. You see, I had never thought twice if I had read, say, about the membrane protein communicating on both sides of the membrane, doing it alone with all other components. I never thought whether I should actually believe these facts if I cannot understand the underlying research or lack time to inform myself about it. I have simply taken it for granted. If published, it has also been peer-reviewed, and therefore I can fully trust it until proven otherwise or sharpened further. Of course, as our understanding of the universe and microcosm similarly obviously shift around as we gather new data. As scientists have moved, particularly in their research on human or animal or bacterial functionality, so deep into the cell that their discoveries have become completely invisible, even more unimaginable to the simple eye and mind, we absolutely need to trust scientists. We need the trust of the wider public into the scientists, because people have a tendency of not to believe and not to trust what they cannot understand. They have to go by the faith to keep their trust, and it is for scientists to keep that faith in scientific methods. It has been wavering in general, and we all know particular cases where people have demonstrated their incomprehension and therefore lack of understanding, which has also led to lack of trust of the scientific thinking. Professor Wüthrich, you may wonder why reading your lecture and looking at the beautiful pictures of proteins organized in the center and floating freely at the outskirts made me to think of trust of scientific methods. Probably Estonians here find it easier to understand. Our society is the world's only truly digital society which needs a secure form of identification over internet to function. And we are facing a risk right now which only scientists are able to describe, and only those who are able to describe it and understand it can actually fix, can remove this risk. The rest of us simply have to accept what they say. Policymakers have to decide on the methods, timing and financing of the remedy measures. They have to prepare for the slight possibility that we shall temporarily be forced offline in case the scientifically proven risks should actually realize in the time frame much too short to take general and universally available remedial action. They will later have to justify their decisions. The costs incurred have to be justified. National auditor will have to look into the case and report to people. It is much harder than, say, reacting to the crisis, let's take one from the quite close past, in aviation resulting from a volcano eruption, when most people can grasp the reality of the risks and accept that costs will be incurred by the society at large while avoiding that risk. In our digital identity security scare, we as a society can only cohere around the proposed solutions if we can trust into the scientists and the methods they apply, both in discovering and in sorting the problem. Yet it is important for the future of our own digital society and for the people in all developed countries where governments, for their fear of unknown, have left their people alone in the cybersphere and refuse to provide them with safety that comes from the possibility to identify yourself securely and with a state guarantee to your partners online. This is what we are facing this week, and we do not yet know when our thrilling and interesting, but also scary to many, fully scientific story meets its happy end. But it cannot, unless we can rely on general trust in science and scientific measures. And that is why those beautiful pictures, making people see, therefore easier to believe, how the proteins really behave, how life truly happens, how life truly exists, which accompanied your Nobel lecture. That's why they were so fascinating to me just this week. I will now give the floor over to you, dear Professor Wüthrich, in honor of the memory of Professor Lippmaa. Thank you for being here with us.
Mrs. President, dear colleagues, it is a great pleasure for me to be here today. It is so that Endel Lippmaa has long ago opened my eyes for the beauty of your country and also let me understand a little bit the special situation in which you live and work in Estonia due to different and ever-changing political situations. My first visit here, upon invitation by Endel Lippmaa, was already in 1973, and my wife and I came back in 1977, and there have been more visits, and we have fond memories. Today, I would like to talk about research along the lines that Professor Lippmaa has pursued during much of his scientific life, namely work in NMR, nuclear magnetic resonance. I would, however, want to widen the scope beyond the technique of NMR. And in this sense, my talk should have impact on politicians as well as on scientists. The message I would like to get across is how important it has been in the past to support basic research which has no apparent immediate goal and which later on, with the availability of new engineering, computational, and any kind of technical advances, all of a sudden can blossom into applications which affect our daily life. I'd like to start by summarizing what we expect today from the use of the NMR principle in daily life. This is not going to be comprehensive. I'm just going to cover aspects which relate directly to medical and pharmaceutical applications. And it is so that the principle of nuclear magnetic resonance can be applied for studies of macroscopic objects, such as intact human bodies, and of molecules. And we are changing the size range by about 10 to the 9 orders of magnitude when we compare studies of a human body with studies of a molecule working within that human body. Let me first indicate what we expect from magnetic resonance imaging today, which is important both in its benefits to those who need medical diagnosis after accidents or changes in their life situation, and on the other hand, it has also turned into a very big economic venture for those who produce the machinery. It has created 10,000 of high-tech jobs in hospitals around the world, and so it has turned into a very important economic factor, as well as a scientific achievement. And this all started in 1972-73. What you see here is an MRI image of my right knee. You can see my name on the left, and it was taken in 1989 when I had a small accident when playing football. And if you want to continue playing football at an advanced age, you better check your knees and other joints. And here you see more recent images of my knees. They were taken in 2016. And you can see two things. One is that the quality, the sharpness of the pictures has greatly improved from 1989 to 2016. And you can also see that my knees are still okay, so that I can still play football today. Not on a very intense level, but you see, once you have a Nobel Prize, there are always guys who take pictures of you, even when you don't play football so well. This is one side. Here, the connection to daily life is obvious. It is quite unimportant that my knees are studied, but in the big leagues of football, the players make intensive use of MRI. Weekly, you read the newspapers and you see which guy had to go to MRI to find out whether he can continue playing or needs a rest. Now let me turn to the other side that we cover in our work, where we would refer to as NMR used in structural biology, and that's the work that Mrs. President has alluded to, that we can study the molecules of life in their natural environment, in solution or in contact with solutions. I'm going to illustrate the kind of works that can be done here with old work that we completed almost 30 years ago, and that is work on the drug cyclosporin A. Now you see a number of technical indications here. So, well, I don't have a pointer now. The drug I'm talking about is underlined. It is cyclosporin A. It is itself, thank you, it is itself a small protein, and fortunately for our well, that's a bit difficult. For our studies, it binds in the cell to a small receptor protein, a soluble protein, so that even 30 years ago, we could actually, with an MR, study the interactions of the drug molecule with its receptor in the living cell. And that's how the structure looks. In dark colors in the center, you have the drug molecule. In light blue, the receptor protein. Once you have such a result, you can remove the drug from the surface of the receptor where it binds, and you can now start to study that receptor crevice more tightly. You see that there are green balls and there are yellow balls, indicating that there are hydrophobic and hydrophilic components which interact with the drug. And then we may go to the chemists and look at the chemistry of the drug. And you see this is an undecapeptide, a cyclic peptide, and it has some unusual side chains. And now it may be that from looking at the structure of the receptor, we decide that some of these side chains may be too big or too small, or it would be better to have a charge group or a polar group instead of a hydrophobic group. And so the chemists would modify the drug, put it back into the system and check whether indeed the expectations from structural biology are fulfilled, that modification of the drug would bind more tightly, the dosage could be reduced, unwanted side effects could be reduced, and so on and so forth. And then, of course, you also want to modify the drug sufficiently so that you can get a new patent, and the old patent runs out, and use the improved drug with patent projection for the next 10 years or so. Again, we are talking here about a product which has turned in more than $1 billion a year for 30 years by now. And several follow-up drugs have been developed, and cyclosporin A is still used in combination with some of these follow-up drugs. So this is the sort of work that we expect today from using the physics principle of nuclear magnetic resonance. These useful applications are based on work that has extended over the last 2 centuries. And that's what I would like to illustrate to you now. You see, there are many open questions. For example, it is not clear why we can at all get sharp pictures of a human body with an MR. We actually only see the water in our body when we look at the image. And all the rest doesn't interfere. And we would like to understand why this is so. And when we understand, then we may be able to improve the technology further. And so I start with the basics of NMR. It's a quantum mechanical phenomenon. Nuclei tend to have a spin. That's a supplementary quantum number. And in the simplest case, we have a spin of 1/2. And if you have a spin of 1/2, then you have 2 eigenstates, which can be distinguished as soon as you apply a magnetic field. So in this scheme, B indicates a magnetic field. If B is equal to 0, then the 2 arrows up and down, which represent the 2 eigenstates of the spin 1/2, cannot be distinguished. As soon as you apply a magnetic field, you can distinguish between the 2. Now, this splitting is extremely small in energy, very small. And they could, for a long time, not be directly observed. It was actually first observed by this man, Peter Zeeman, in 1896. And what Zeeman did was to look at optical spectra of materials that contain magnetic nuclei, and then he put this material into a magnet and discovered that there was fine structure in the spectra that was not present in the absence of a magnetic field. And he published this, but he had trouble because for some reason his thesis advisor had strictly prohibited all people in the laboratory from putting anything into a magnet while recording optical spectra. And so he lost his job in 1997 because of disobeying the boss. In 1902, he got the second Nobel Prize in physics for this observation, and then his PI was sacked and he became the director of the institute. It's a good story for students that they should not listen too much to their professors, but most of all surpass their professors with their achievements. Now, this was in 1896, and it took another 60 years until it became technically possible to directly observe transitions between the 2 Zeeman levels. And this became possible because of the work done by thousands and thousands of scientists during the Second World War who were developing radar technology. There were about 5,000 scientists in the United States alone who worked on radar technology, that is microwave and radio wave technology. And Germany had hundreds of scientists working on this. Russia had many working on this. And when these scientists came out of the war, they immediately applied the knowledge that they gained with this radar technology to develop spectrometers that could now detect these very small energy differences between the Zeeman levels directly. And you see the relation here, this energy difference can be expressed by frequency, omega 0, and omega 0 is proportional to B0. Okay, and B0 is the magnetic field. So if you apply a stronger magnetic field, you get a larger Zeeman splitting than if you apply a weaker field. Now, when the physicists first performed the NMR experiment, they thought that it would be good for only one purpose, namely to obtain a more precise, this is getting a bit difficult, a more precise measurement of gamma, the gyromagnetic ratio, which relates the frequency of the transition is the magnetic field. That's all they thought it would help. And these were Felix Bloch, a student of CETH, who then worked in the United States, and Edward Purcell. Those two independently, within 1 month, published an NMR experiment. One worked on the West Coast in Stanford and the other at Harvard on the East Coast. And both thought that all they would contribute was a more precise measurement of the gyromagnetic ratio. What happened then, within a few years, the chemists found out that spectra of first organic molecules would reflect the chemical structure. And between 1950 and 1970, NMR became a widely used method in physics research. It is amazing how many physics Nobel Prizes after 1950 have been largely due to using some sort of NMR experiments in solid-state physics, in low-temperature physics, in studies of phase changes and so on, and of course in chemistry as a widespread, with widespread use in analysis of organic and inorganic chemical compounds. Felix Bloch spent his last years in Zurich, and he visited my lab several times a year between 1970 and 1978 when he passed away, and he couldn't believe what was happening beyond measurement of the gyromagnetic ratio of the proton and other nuclei. And of course, during these 20 years, a lot of research has also been done here in Estonia, in particular by Professor Lippmaa and his group, specializing in methods of solid-state NMR, which I'm not going to cover here today. I'm going to now try to let you see how this basic work led first to getting images of macroscopic objects and then images of macromolecules. You recognize this particular chemical, I'm sure. It's water with the two white balls representing the hydrogens which we observe in the NMR experiment. And that gives one line. That's it. Now, this line can contain a lot of information. I personally spent 3 years in California looking only at this line, in studying water interacting with paramagnetic meadowlines, with all sorts of compounds. And if we had been a bit smarter at the time, we would have patented our results and we would be millionaires today, because the work that we did on the interaction of paramagnetic meadowlines with water is now widely used as contrast agents in magnetic resonance imaging. There are others who have made some money later on. Now, there are smarter ideas than just looking at the effect of other chemicals on the water resonance. And the idea is to apply not a simple static field to a macroscopic object, but to apply a field gradient in addition to a strong magnetic field. So that the field next to the right ear of this person is a bit different to the field next to the left ear of that person. And so if you can see only the water resonance, a single line, then this single line will appear at a slightly different frequency near the right ear or the left ear. You see, when you change the magnetic field, the Zeeman splitting changes in proportional to the magnetic field. And so across the head we can distinguish between water outside of the human head, water next to the right ear, and water next to the left ear. Now, if we take not just 2 points, but say 120 points across the head, And then we repeat the experiment by applying a field gradient from the back to the front and from the top down, so in all three dimensions of Cartesian space. Then we can get an image of the head with ever-increasing resolution. It needs quite a bit of mathematical treatment, but that's what it is. And all we see is the water. And why this is, I will come to a little later. The two colleagues who got the Nobel Prize in medicine for the invention of MRI are Paul Lauterbur and Peter Mansfield, who got the medicine prize in 2003. Now when we turn to studying proteins or other macromolecules, we have a different situation. When we worked with the water line, we had interest in making the spectrum more complicated by applying a field gradient and making 120 lines out of a single one. Now here we have hundreds of chemically different spins, and we get a mess. We don't get a single line, but we get a lot of lines, in this case about 800. Of these 800 lines, only about 20 are well separated. And from studying these well separated lines, we recognized already in 1968, I think I published the first paper on this particular protein. It was clear that NMR could do the job of getting a structure determined de novo, provided that we could resolve the middle part of the spectrum where several hundred lines are overlapped. And the solution to this was to introduce an artificial second time axis into the laboratory. I mean, you have the time which made you age minute by minute, and now you apply a second time artificially perpendicular to it, and then with a two-dimensional Fourier transformation go into two-dimensional frequency space. And now you can see that in the plane we have nicely separated lines again. And for this achievement, my colleague Richard Ernst got the Chemistry Nobel Prize in 1991. Now there was another problem to be solved before. Now we had the resonances, they were resolved, but we had the following problem. There is the so-called Brownian motion of particles in solution. And this now goes back 200 years to Robert Brown. Now, 190 years to be exact. Now, Robert Brown was a botanist. And as a botanist, he had a microscope and he played around with grasses and with flowers and things. And one day, he lost some pollen from a flower into a beaker with water. And curious as he was, he looked at suspended pollen on the water and discovered, to his big surprise, that these pieces of pollen weren't just sitting on the water, but they were moving around. Smaller pieces would change direction more frequently than larger pieces. And the movements were not predictable, they were completely random. And so Brown published this and didn't understand what was going on, but found it interesting enough to publish. These frequencies, the frequencies at which the direction of these movements changes, is of the order of 10 to the 10 per second. So now imagine you want to get a sharp picture of an object that moves at this frequency, randomly, not periodically. If it were periodic, it would be trivial to get sharp pictures. But it's random. Now you take photographs of moving objects, And then you know that you need a short shutter speed to get a sharp picture. But there we are talking about maybe 10 to the 3, 10 to the 4 per second in frequency of the motion. That's 6 orders of magnitude away from here. So when we started to work on the structure determination of proteins, the crystallographer simply laughed at us and said, no way you'll ever get a sharp picture. This stochastic high-frequency motion will blur the picture. And so it took a bit of reflecting to find scalar quantities, that is, quantities which are invariant under rotation and translation. And if we could find quantities that are invariant under rotation and translation and could be measured by NMR and are quantities that determine the three-dimensional structure, then we could solve the problem. And now it is so that the distance between two atoms is such a scalar quantity. You see, I show here circles. Each circle represents an atom. And the line between the two atoms is the distance between these atoms. Now, if I can describe the distance between any pair of atoms, then obviously I have determined the structure. It's quite clear. And the distance between the two atoms is independent on the translation across this image or the rotation. It doesn't change. So if we are able to measure a large number of such distances and then develop the necessary mathematical tools, then we can determine the three-dimensional structure of the molecule. There is a quantity in NMR, the nuclear Overhauser effect, NOE, which is proportional to the distance, to the inverse 6th power of the distance between pairs of atoms. Now again, Overhauser was a physicist. He proposed this experiment in 1953. He used it in solid-state work, actually in metals. With electron spin resonance, and he found the Overhauser effect between electrons and nuclear spins. And we then applied it between two different nuclei, therefore nuclear Overhauser effect. But again, Overhauser did his work, and see, this is basic research. He was curious to find out how dipolar coupling between electron spins and nuclear spins would affect things in his experiments. Now, a two-dimensional NOE spectrum of a protein looks like this. There are hundreds, nowadays thousands of peaks, and each peak represents a distance between two atoms. And after about 6 years of development of algorithms and programs, and program these algorithms, we could turn this spectrum into three-dimensional structure at high resolution. I mean, just to give you an impression of what it means, when we span a distance space with the information from the NOE spectra, we generate a distance space of about dimension 10,000 to 30,000. And then we embed the protein structure in this high-dimensional distance space and then project the structure back into three-dimensional Cartesian space. That's in very short words what it means. It also means that we were given the biggest computer at CTH for 3 months to do one calculation. Nobody else could touch the computer. That was in 1983, and that's how we could turn this out. Today, the same calculation would take less than 1 second. That's that's how things go. Well, that was also enough to get the Nobel Prize in 2002 for protein structure determination. Now, this is not quite all. I have to go back again by 110 years to go on from here. But this slide was drawn around 2002, and by that time, about 6,000 structures had been solved by NMR. And all the structures were smaller than molecular weight, about 30,000, and most were much smaller. Because the technology that I just outlined worked well for sizes of molecules with molecular weights from about 3,000 to about 20,000, 25,000. And then we couldn't work anymore. So, for example, if we extract the membrane protein from the membrane and solubilize it in mice cells or in nanodiscs, we get a molecular weight of at least 60 kilodalton, usually rather 100 or 120 kilodalton. And so there was no way. We wouldn't see a spectrum. It would just be blank. So we had to go back to Brownian motion. And it needed a particular brain, namely Albert Einstein, who understood what Mr. Brown had seen. Einstein understood that these random translational motions came about because of the thermal agitation of the solvent molecules, which are much smaller than the solute, in this case the protein, and undergo very fast thermal motions. And so there's a constant bombardment on the surface of the protein, and statistically there are always an unequal number from left and right, or top and bottom, and how the molecule reacts. And the small particle has less inertia and it changes with higher frequency than a larger particle. That was the first thing that Einstein found out. He was working in Bern, a few kilometers from where I grew up. He was very bored. He actually was standing at the lectern writing patent applications. He was in the patent office in Bern because he couldn't find another job. And so in May 1905, he published this explanation of the translational Brownian motion. And then some of his colleagues discussed this with him, and then he had a second idea, namely that when the impact of the solvent molecules was not exactly perpendicular to the surface of the sphere, but tangential, then the collisions with the solvent would not only induce translational motions, but also rotational motions, which Mr. Brown could not see under the microscope, of course. And so he published a second paper, and here you see the first paper appeared in 1905. The second one was submitted in December 1905 and appeared in 1906. Now, you see, when you talk about Einstein, then you think about relativity theory and the magneto-optical effect. But Einstein himself, he talked about the Brownian motion when he gave lectures. And this in particular is an invitation to, this is a report on a lecture that he gave in Bern. And he talked in a restaurant in the Storchen, and there were exactly 20 people in attendance. So imagine this, Albert Einstein gives a lecture in Bern, and 20 people managed to get and listen. And then the text gives a brief summary of what he has found. He said microscopically small non-living parts which were suspended in liquids move irregularly, he means stochastically in English, and are all the more vivid the smaller the diameter of the parts and the viscosity of the liquid and the higher the temperature is. Brownian motion. After a short explanation of different attempts to explain, the lecturer derives a simple formula for the distances the parts are traveling with the help of the kinetic theory of heat. And for us now, these findings are summarized in the Stokes-Einstein relation. Essentially consists of defining a correlation time tau c, that's at the bottom of the slide. This correlation time essentially tells how long a time has to pass by for the particle who is stochastically moving to forget about its past. So after the time tau c, there is no memory, it starts all new. Now it is so that this correlation time determines the important spin relaxation parameters in NMR, T1, T2, and the nuclear Overhauser effect. Now those of you who have had an MRI made of parts of your body, then you may recall that you were shown T1 weighted images and T2 weighted images. And now we immediately understand why MRI works and why we see only the water. Because the water molecules are the only molecules in our body which move fast enough to be seen by NMR. Bones, fat, muscle doesn't move and you can't see it. Simple as that. And so once you know about this, then you can continue to develop refinements of the MRI method, and for example, with the use of paramagnetic agents to enhance effects of blood flow and so on. Now, for us in structural biology, these considerations that are based on Einstein's theory can be extended to the description of the way spins behave with time in our experiments, and from this we derived a method that we call TROSY, transverse relaxation optimized spectroscopy. So in imaging you have T1 weighting, T2 weighting, and we are now doing T2 optimization. And now all of a sudden, instead of having a limit of 25 kilodalton for studies with NMR in solution, we are at 900,000. So in one step, 30 to 50 times higher, because under certain circumstances we could uncouple the appearance of the NMR spectrum from the Brownian motion. Again, the theoretical work leading to this technology has been described by others in the early 1960s. And of course, just as Einstein had no idea that his work would ever affect NMR, or even Mr. Brown in 1826, or all those who provided us with this basic knowledge, they had no idea that we would one day study proteins or make images of live bodies. And so here we are, and of course we go for application. This is a spectrum of a particle of 870,000. But the important thing is that we can now study membrane proteins. See, and now we can take the protein. There are essentially two kinds, either alpha helical membrane proteins or beta-barrel membrane proteins. And now we can take these out of the membrane, put them into micelles and get spectra, get NMR spectra, and apply the technology where it is needed. I just tried to explain to you what may be needed when you study membrane proteins. Again, Mrs. President has alluded to this. She is wondering how does the effect of a drug that bites outside of the cell, how does the drug signal across the membrane so that follow-up reactions will lead to help fight disease, or in most cases. Well, what happened this is a G protein coupled receptor. Okay, this receptor goes across the membrane. You see the outer and the inner surface of the membrane, and inside the cell there is a G protein and there is beta-arrestin. And now we want to know how can the chemical structure of the drug, that's shown in green at the top, how can this now signal specifically either to G protein or to beta-arrestin, or to kinases? There is a third class of proteins that are affected. Now, crystallography has provided us in the last 10 years with about 35 structures of human GPCRs. The human body contains about exactly 826 different GPCRs. They do just about everything: smell, taste, heartbeat control. I mean, all anything you can think of is governed by interactions with GPCRs. And so, when you do a crystal structure of such a protein, then you have to modify it. This protein moves a lot. It's flexible, it moves. So, to get crystals, which lasted for the search that lasted for several decades, you have to exchange certain amino acids, and most of all, it turned out that you had to attach another protein, rather large protein, to the GPCR in order to get crystals. And then you freeze that modified, when you get crystals, you freeze the whole thing down to liquid nitrogen temperature and record the spectra. In other words, the natural flexibility of the proteins must be blocked in order to get a crystal structure. But on the other hand, from the crystal structures, we get an overall view of how the protein is built. And so we can now take the crystal structure and start to put NMR probes, as we call it, in strategic positions. For example, here, you see the two red dots here. I hope I can hear. Okay? So we knew from crystallography that something was changing here between an activator and an inactivator, when we bind an activator or an inactivator. So we put NMR probes here, and then we go through a library of different drugs that we bind on top. And now we work at body temperature, and with a non-modified protein, we have now, again, we have returned to the wild type protein, and we study how the signaling to the G protein and beta-arrestin is governed by the different chemistry up here. Now, if we have a drug, then usually the effect of the drug, the wanted effect, goes either through G protein or through beta-arrestin, but not both. Usually, if we get the benefit from signaling through the G protein, any leakage to beta-arrestin will cause unwanted side effects. And so we can now use this sort of observations to modify the drug in attempts to get pure signaling through only one pathway. And this is the sort of thing that we can now do with this technology when we work with membrane proteins. At the moment, my groups in California and in China are exclusively working with this class of proteins. So, you see, this is a result of basic, we have to talk about drugs and getting close to the bedside, otherwise we don't get money to perform our research. But of course this is based on what Mr. Braun has observed in 1826, what Einstein has discovered in 1905, what Bloch and Purcell have achieved in 1946, and so on and so forth. And if we don't support basic research today, which seems not to yield anything interesting in terms of money, then we will not have something new coming out of new technologies 10 or 20 or 30 years from now. And now I have talked to Mrs. President primarily and the other politicians who may be here. Thank you. Okay.
So please, discussion is open for questions about different things. Okay, just to warm up, I would like to ask a question, because I know there is a lot of students. Maybe you have some recommendations how to get the Nobel Prize.
Well, you see, I was once recently asked to give a keynote lecture in China at the meeting where, I mean, the NA National Academy was represented, the Royal Society was represented, and what the Chinese wanted from us is to tell them how to evaluate their research. See, it is a very curious situation in China. They invest billions and billions of dollars now in buying equipment, in hiring people to do research, and they do not have even a primitive evaluation system. What they rely on is that that someone can publish a paper in Nature. If he can, then he's here. If he does not, then he's here. And that's, of course, no situation for a nation who wants to become a leader in scientific research. So in my lecture, I showed the picture where I was training high jumping some 60 years ago. And I was then published in Nature, training high jumping, because I told them, look, teach your kids to do some measurable, anything measurable, really measurable. I like high jumping. You know immediately whether or not you succeed. If you don't succeed, you still have to continue. And you have to recognize that you don't succeed. And or you can run 100 meters and you'll be beaten. You don't want to be beaten, so you train again and you do better. In science, unfortunately, it is not so clear. You may even fool yourself by thinking that you got a big result. But just teach your kids to play, do some sports, and learn what it means to succeed in a competition. And that's what you should consider when you do your science. You should be first, but you shouldn't study for a Nobel Prize. It's far too much fun to do science to think about such side effects.
Now, please. Yeah?
Thank you for a very inspiring lecture. So I have a question about your vision about the future of NMR technique.
Well, sir, you see, I prefer to predict the past. That's much safer. But when we now look, what will happen? I mean, functional imaging has not yet reached the clinic, essentially. Functional imaging will undoubtedly come into the clinic within the next 10 to 20 years. On the side of structural biology, much may be gained by using detection of less sensitive nuclei. You see, today we detect everything on hydrogens. I'm now getting a bit specialized, but and there have been ideas to detect even nitrogen-15 instead. And when you go to very high fields, then you can greatly benefit if you detect non-hydrogen nuclei. And then you have these tremendous improvements of the sensitivity by essentially by the Overhauser effect again between electrons and nuclei and nuclear spins. And if you apply this sensibly in the right place, it's in these directions that I see realistically progress in the coming 1 or 2 decades.
So, please.
Yeah, so as a structural biologist, it is kind of nice to know that NMR is still in development. Synchrotrons are being built, so I know that my bread and butter are not going anywhere. But what I'm wondering is if NMR is going to be, or remain actually, a sort of complementary method to, say, X-ray crystallography, which is producing most of the structures of protein data bank. Thank you.
Okay, the numbers are that by today, about 110,000 structures have been determined by crystallography, about 14,000 by NMR in solution, and now more and more structures are coming up by cryo-electron microscopy. That's a big fad at the moment. What cryo-EM will not bring is information on the dynamics that we can get with NMR. So I expect that the complementarity of the methods will continue to be the way to go. See, for example, with GPCRs, we could in principle get into de novo structure determinations, and we may in the future. But at this moment, crystallography is doing such a great job in getting the overall architecture done that it makes much more sense to concentrate on studying the dynamics as a complement, the dynamics at body temperature with a natural protein in combination with studying the architecture of the modified, rigidified protein at very low temperature.
So as you said, we know now 150,000 structures.
About, yeah.
And yet we don't still understand how proteins are folded. We don't understand how proteins, or the principles of proteins and nucleic acids interact. So what is missing?
I'm talking about this the day after tomorrow in Budapest. Well, it's a very good question. I mean, why can we not, after experimental structure determination of about 150,000 different proteins, learn enough to develop force fields that would enable us to fold the chemically known polypeptide chain into its functionally active form? It's a very good question, but that's where we are. There have been, I think, the most forceful approaches have been made by Baker's group, whom you may have known. And Baker, you see, these are tremendous computational problems comparable to weather forecast, so in size of the calculation. And so for years, he would use computers all around the world by just asking a large community of computer users to let their free time be used for his calculations. It didn't work. It didn't converge, not once. And then he started to take in distance constraints, few distance constraints, and it works. So then it gets very close. And we have shown, I must also say that we have shown already in 1982 that we can reduce the number of constraints for a small protein to about 3 per residue, and we would essentially always get the correct fold. So it needs relatively little, but for some reason, force fields have not so far allowed to really predict the structure de novo. It's moving, but it's not there yet.
Thanks. Before we continue, we thank Mrs. President for attendance, and she has to leave. So I see a next question, please.
You talked about these structural studies, and you mentioned that there's a lot of information available about the formation of the structure and about the interaction of different macromolecules. But the question is, how important this knowledge would be to understand how the cells are designed and function?
Well, you probably ask about the point in time when we will be able to determine the structure of a complete cell.
Not the structure, but the functional principles, so that we understand how the cells really are put together in functional terms and how they are functioning.
Yeah, but
As a holistic unit.
you see, when you read journals on cell biology, then you will see a lot of drawings with balls and squares and moons, ellipses, and these are dreams of the cell biologists where they assemble these balls and pieces and bits. And each one of these pieces is a structure, but they don't have the atomic resolution yet. And so we are on the way. You see, today, 30 years ago, the structure determination of one small protein could make the cover of cell. Today, we have to at least study complexes of 2 or 3 molecules. And work is going on in the direction of what you ask, to assemble at low resolution polymorphic structures that may contain 20 or 30 proteins, pieces of DNA, some lipids, and so on. This work is progressing. And I could imagine, well, some say that even today we have low-resolution pictures of intact cells. And I could imagine that within 20 years or so, we would have a rather complete description with, you see, this will be integrative work. This will be work using different techniques and assembling this all into one picture. And research is on the way. It's ongoing, but I wouldn't say that we are yet there to describe a complete cell at atomic resolution. Then once we'll have done it for the cell, you'll ask, but how does the arm function, okay? Or a piece of a lower organism. Rightfully so, of course.
You're living in the synthetic biology area.
And then you get into the synthetic, this will be the confirmation, of course, but synthetic biology will have to rely on knowledge obtained by analysis of the natural system.
So, some more questions? Yeah?
About the structure of proteins. I understand that
Why don't you take a microphone?
just a question about structure of proteins. The force field probably is not the full answer. It must supply the stability of the protein, but not necessarily determine how it is folded, because cell has many other ways to constrain this process of putting it together into active form. How far we are there? What we could do there? How far we are in this way to understanding that? And what could NMR give to that?
I think, you see, to understand, if I understand you correctly, then you are distinguishing between a folding pathway of protein and thermodynamic stability of the resulting fold and so on. And when you want to understand this process going on in the cell, then you have to consider that there are a lot of partners for the protein. The protein, I mean, the nascent protein will be associated with the ribosome, with the surface of the ribosome. There will be, you know about chaperones, you see. So it will not just float freely in solution, it will be, first it will be associated with the ribosome, then it may be taken up by chaperones, and so the folding process goes under variable conditions characterized by interactions with a variety of other structures. And then, of course, you end up with a structure, and it has you know the name of Ostwald, who was a student here in Estonia, and he got the Nobel Prize in, I think, 1910. And he very clearly formulated that a chemical process can be catalyzed so that it runs faster, but the catalysis will not affect the stability of the end result. And that's how you have to think about protein folding pathways versus the stability of the folded protein.
Some more questions?
I think the audience has had enough.
Okay, yeah. So thank you very much for this presentation, and then questions. And now we have some short presentations from some people who were invited to say a word. And please, President Tarmo Soomere, your floor.
Thank you very much, Professor Wüthrich, for this, I would say, inspiring lecture. And I must say that a distinguishing feature of lecture of nobelists is that I can understand them, even if I'm not expert in the field. I think partially it is because you're training also in mathematics, additionally to chemistry and physics. But anyway, it was an impressive and very nice talk. But I really would like to add a few words or nuances. Of course, normally scientists, they prefer to be outside of spotlight, but I think they all like to be sometimes recognized and awarded like all other people. And this sort of tradition in Estonia includes distribution of annual national science awards in 8 disciplines. I think some 24 of people here have received that prize in different times. And then 2 awards for lifelong achievements, and 1 award for exceptional discoveries. They're all financed by state from the budget of Estonian Ministry of Education and Research. But today you have a bit different event. So the process of awarding is particularly pleasant for participants when there are some additional resources to play with. And those resources can make events like today attractive, professional, memorable, and maybe in some sense unforgettable. And those qualities are quite often used when private sponsors enter the system. And then this lecture, Endel Lippmaa Memorial Lecture and Medal, are the first example of a prize decided by science community but sponsored by private persons and enterprises in Estonia. So today's event wouldn't be possible without their support, for which the Academy is very thankful. The list of sponsors is tabled in the foyer and also indicated on our website. And this adds another nuance into today's event. We have been long talking in Estonia about very limited support of Estonian science to our industry and thinking about how we could convert our research results into economic progress. And by sponsoring today's event, people from industry have made very strong move towards building such a bridge by saying that in material form that they are willing to support science in Estonia and visibility of science in Estonia. So it's now time for scientists to take their move. But that was a question how to achieve Nobel Prize. So I don't have a good answer, but I can a little bit explain maybe how close Estonia or Estonian scientists are to Nobel Prize, if you can measure that. It's not measurable, I know, but still there are some ways. So the oldest medal and second prestigious, as said by many, is a Copley medal, starting from 1731. And the winners of Copley Medal and Nobel Prize are not that much different. So today the list of Copley Prize recipients includes as many as 52 Nobel Prize winners. And that's just to give some flavor, who are the Copley Medal laureates? 2 years ago, 2015, it was given to Peter Higgs, for, of course, you know for what. 2016, it was given to Richard Henderson, for his development of electron microscopy of biological materials, which is somehow sister discipline of NMR. And last year it was given to Henry Wiles, who is not very famous. It was given for his new and excellent proof of Fermat's last theorem. Henry Wiles, so Peter Higgs has got Nobel Prize 2013, but Henry Wiles probably doesn't have much chances to get Nobel Prize because he's a mathematician. So Copley Prize and Nobel Prize are somehow close to each other in some qualitative terms. And when we turn to Estonia, Estonia is small, of course, but beautiful, we think. And this, I mean, being small, is quite often our excuse for having one relatively small number of international recognitions. But it's not widely known that one Estonian scientist has been awarded the Copley Medal. It's strange that this information in German language Wikipedia is visible from the start of the relevant article. In English language Wikipedia, it's hidden in footnote, and into Estonian language Wikipedia, it was added just July this year. So the reasons are not easy to explain, but I think that there is a misbelief that Estonian science is so small that it would be never able to win a sort of Nobel Prize or global recognition, which is totally wrong. And now coming to that Estonian scientist who has won the Copley Prize, everybody in this room knows his face, because it was printed on the 2-kron banknote. For 2 decades we used that. That was Karl Ernst von Baer. He received this recognition in 1867, so we could celebrate this year 150 years of an Estonian scientist, not exactly Estonian by nationality, but scientists from Estonia having this sort of recognition. And of course, his masterpiece is development of embryology and comparative anatomy. But he is one of the very few people in the world, and probably the only Estonian scientist in the world, whose discoveries made 200 years ago are today being taught in standard textbooks on university level. It's sort of quite unusual thing. In textbooks, university level, you have much newer results normally. But trying to explain then, or to measure how close or how far we are from Nobel Prize. It was already mentioned Wilhelm Ostwald. He is the only Nobel Prize winner who has ever worked really in Estonia. He got his doctoral degree in University of Tartu and was private docent there until 1881, and then went to Germany. So we can think that we own, say, 1/3 of Nobel Prize. We have to share him with Germany and with Latvia. But much closer hit came just recently. One of the 2 recent laureates of Nobel Prize in Economics, Bengt Holmström. He's technically born in Helsinki, Finland, and part of the Swedish-speaking minority in Finland. But not many know that he has at least one quarter of Estonian blood. So this sort of speculation may lead us to completely non-scientific, but correct in terms of bibliometry conclusion that we are very close to winning one single Nobel Prize. That was answer to the question from the audience, which, but we can't give any rules how it could be done. But to go back to more serious things, so Endel Lippmaa definitely belongs to the pool of most excellent Estonian scientists of the entire 20th century. A large part of his career was performed when Estonia was incorporated into the Soviet Union, and which is even more important, also stressed several times today, a substantial part of his activities actually were contribution to the building of independent Estonia. And we shall never know, unfortunately, how sparkling and influential could have been his research if he would have been able to be dedicated only to science. But perhaps the strongest message for young people from the life and career of Endel Lippmaa is that you really can be highly successful and influential in the world science, even if you happen to live in wrong time or in fairly unfavorable conditions for cutting-edge research. It doesn't really matter how small the nation is where you come from. So similar proofs have been given, for example, by Svante Pääbo in evolutionary genetics or Endel Tulving in experimental psychology. And in more recent examples, just several Estonians have happened to be on the cover of science magazine, so Tambet Teesalu a few years ago, and Jüri Niinemets just a couple of weeks ago, and the development of scientists from Estonian Biocenter were listed among the runners-up for Science Magazine Breakthrough of the year in 2016, so being among the top 10 in the world, it is not far from really important international recognition. And of course, as I was telling, every nation may give birth to world's leading experts, scientists or different creative persons. And we do have some competition with our neighbors in Finland in this respect. The Finnish academician Markku Kulmala is now 6 years in a row the most cited person in environmental sciences in the world. But we're not lagging behind. We have also sort of secret weapon in our academy. Arvo Pärt is in 6 years in a row the most performed living composer in the world. He has already received a prize called Premium Imperiale from the Japan Emperor, which is often called Nobel Prize in Music. So if I may again non-scientifically and linearly interpolate those achievements into the future, I think it will be just a matter of time when the Nobel Prize hits some of Estonians. Thank you very much.
Thank you. Now, following our program, the floor is for academician Mart Saarma. As Finland was already mentioned, you all know that he is actually based in Finland, but he has been always Estonian scientist. Am I correct?
Thank you very much, President, Professor Wüthrich, Dr. Endel Lippmaa, and Jaak and Mikk, ladies and gentlemen. I'm really very honored to stand here in front of you to say a few words about academician Endel Lippmaa, a man I greatly honor and respect. I would like to use the opportunity also to congratulate Kurt Wüthrich for the Lippmaa medal and also for delivering a wonderful talk which we immensely enjoyed. My account will be very personal, very subjective. I will walk back to the years I met Professor Lippmaa first time, and that was in 1969. I was then working at the University of Tartu in the laboratory of late Artur Lind together with Richard Willems. They were my supervisors, and we were these days trying to understand how the protein synthesis machinery, ribosomes, is built up. And we actually found that the RNA in this organelle is very interestingly organized, and we wanted to analyze RNA, but we were missing one enzyme, and that was phosphodiesterase. That is an enzyme which can cut nucleic acids to the elementary building blocks to nucleotides. And we heard somewhere that in Tallinn at the Institute of Cybernetics, or computer science if you wish, is Professor Lippmaa, who is working on enzymes, and he might have the enzyme. So on one Friday afternoon, after phoning him, I met him. I went to the lab, which was at that time located at the Ravala on the first floor, and there was a doorbell which I should have ringed, but I forgot that, so I opened the door and the alarm bell was ringing. It was awful. Everybody jumped out from the lab, and among others, also Lippmaa, quite angry. I was probably so scared that he treated me well, and we had a half an hour discussion mostly about my work. And already at that time I understood that this is a very special man. Knowing that he is fluent in physics and chemistry, I suddenly realized that he's also very fluent in modern biology, in particular in proteins and enzymes. A few years later, actually in 1973, as many of you in the audience know, biology witnessed a major discovery. In Stanford, Boyer and Cohen demonstrated how to clone genes. And actually, genetic engineering was born. Much of what Professor Wüthrich today told to you would have been impossible without producing proteins in quantities, especially with labeled stable isotopes. And a few years later in Cambridge, Fred Sanger taught us how to sequence these genes. We now know that these two discoveries have actually completely revolutionized biology, but also biomedical science, and these, as modern vocabulary says, radical innovations gave rise to the new industry, which is now flourishing with the markets of a couple of $1 trillion a year. One day in 1975, Professor Willems and I were also in this room trying to explain to the colleagues of the academy, mostly biologists, how important gene technology is. Well, we would have left the room with a shame if Professor Orvikko wouldn't save us. He thought that genetic engineering, what we were talking about, is something real, whereas the majority of the audience thought that we are talking fairy tales. And that was 1975. And in years 73, 74, and 75, every number of Science and Nature was full of tabloids about genetic engineering. Lippmaa was different. Lippmaa knew exactly what is going on. He had already at that time a plan to build an institute to join genetics, chemistry, physics, to have the opportunity to tackle biological problems with exact physical methods. So much with his help, we organized a lab at the Institute of Physics. As many of you know, these days University of Tartu, differently to the overall perception, was not the place to do science. It was a very politicized organization, but Academy of Science offered reasonable conditions to do science. Very soon, Lippmaa started to organize a new institute, which we know now, Institute of Chemical Physics and Biophysics, and which is now under the very strong threat to being joined with a university, technical university, without any content analysis or without any reasonable conclusion that this fusion would improve science in Estonia. I would say rather on the contrary. So while organizing the Institute of Chemical Physics and Biophysics, Lippmaa was also very active in organizing international meetings, among others, the famous Ampere Conference, but also, together with Riivo and Tõnu Karu, whom I also see in the audience, he organized exhibitions of modern scientific instrumentation. And that was a unique opportunity these days to get instruments which were used in the normal laboratories around the world. So in 1980, we started the new institute, now Institute of Chemical Physics and Biophysics, with Lippmaa running the chemical physics laboratory, late Aavo Aaviksar running biochemistry, and me running the molecular genetics. And then we had also a lab in Tartu, which was run by Richard Willems. So many people these days and later also ask me, how was it possible to work with Professor Lippmaa? Because he was so strong, he had a strong will, and he was very dominating. I can completely assure you, and I think Richard shares my view, that he gave us complete freedom. We could do whatever we want. He supported us. He created for us conditions. We agreed on basic principles, but otherwise we had carte blanche. He gave us support at every level. Already in mid-80s, although it definitely was some sort of competition, was strongly supporting the establishment of Estonian Biocenter, later the Estonian Genome Foundation, etc. Much of my contact with him has been scientific. He was definitely for me also as a role model, as a scientist, because if you honestly look back in 1980, I still wonder how is it possible that he published seminal papers which are today, still today, highly cited in the conditions what we had. This deserves a lot of respect. Although most of my contact with him was scientific, I had one and quite juicy political contact. And that was in 1991 already. I was running the institute in Helsinki, and I took the rector of the University of Helsinki and also the vice rector to Estonia to sign an agreement with Academy of Sciences and to go next day to Tartu to sign an agreement with University of Tartu. Unfortunately, we have chosen a very wrong moment because on the next day we arrived was an August putsch. And you can probably understand that the rector of the University of Helsinki and vice rector wanted to return as quickly as possible. And there was one obstacle between our return, and that was Professor Lippmaa, because he said that you don't leave before I give you one very important paper. And the paper was the Estonian Declaration of Independence. So, sweating when passing the border, we took 3 copies of the Estonian independence, and next morning with great relief I phoned back to Lippmaa and said that the mission has been accomplished. What is a Lippmaa phenomenon? This is erudition and knowledge. He regularly read Science and Nature, not only nuclear magnetic resonance or physics or chemistry, but rather broadly. He understood the basic problems of biology, environmental science, not speaking about chemistry and physics. Shortly, maybe 4 or 5 before he passed away, in this very room, he delivered, with already weakened voice, his speech. He told to the members of the Academy about the work May-Britt Moser and Edvard Moser have done in Norway, telling that they have discovered the greed cells in the brain. Lippmaa was smart enough to understand that this landmark discovery will shape the future of the neuroscience. Thank you.
thank you, Mart, for fantastic comments on some period. So we have now last speaker of this session, Dr. Nagel, who is the director of the Institute of Chemical Physics and Biophysics. Please.
Dear President of the Academy, dear professors, ladies and gentlemen, on behalf of the National Institute of Chemical Physics and Biophysics, first I would like to thank the Estonian Academy and the organizing committee for establishing the Endel Lippmaa lecture series, and I thank Professor Wüthrich for the most interesting talk. Thank you. And I would like to say a few words about our institute today. At our institute, we try to carry on the high research traditions of Endel Lippmaa and always address the important questions in science. And before starting something new, we ask the question, what's the purpose of it, and try to see how it fits in the broad picture. And the broad picture gives us the bigger goal for what we want to achieve. And I have an example from the past. And, well, I remember when I came to the Institute in 1981, then a couple of weeks afterwards, Endel Lippmaa said to me, yeah, you can do your experiments in the blue magnet. We have decided that we can use it for the physics experiments, but before that there is an important measurement to be done. We need to precisely determine the mass difference of helium-3 and tritium using high-field ion cyclotron resonance. And once we have done it in a couple of months, our friends have measured the maximum energy of the escaping electron from the tritium beta decay reaction, and then we can calculate the rest mass of the neutrino. Well, all my colleagues were older, and my older colleagues at the coffee machine then were joking that, yeah, well, when accomplished, that will be a very good candidate for the Nobel Prize. Of course, it was a complicated task, and the maximum energy of the escaping electron in the tritium decay reaction is still not very well known. But some years later, Endel Lippmaa started the Estonian collaboration with CERN. And now the group of Martti Raidal is a member of the CMS collaboration of a Large Hadron Collider. And they were very much involved in the work that led to the discovery of the Higgs boson, and that's about as close as we got as an institute to the Nobel Prize. And now Estonia is on the way to become a member of CERN, and Estonian high technology companies will soon be able to compete for the CERN infrastructure orders, and that would be important. And I think that bringing up the idea and popularizing the CERN membership might be the most important single contribution of our institute to the development of the Estonian society in the recent years. And that shows us where the strength of our institute is. It is in the excellence of our research. We have several visible fields of research today. Some were studied by Endel Lippmaa, and others have emerged later when young and brilliant people appeared. We attract young people who have studied in well-known universities as postdocs or obtained their PhDs in places like Oxford or Kyoto. And they come to us because they feel the vibrant research atmosphere and see the opportunities that are opening up. And of course, we need to encourage them in their work so that they can recognize the new and unknown. exciting future. Thank you very much.
Nii, sellega on meie tänane programm lõppenud. Ma tänan kõiki, kes osalesid. This is the end of our today's program. I'm very grateful to everybody participating. And I hope that the Academy will organize such outstanding lectures in future, and you now know that this is worth to come. So veel kord suur tänu osavõtu eest ja olete oodatud meie järgmistele väljapaistvatele sädelevatele loengutele. Aitäh!